Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. Today, our group is going to present you our presentation about simple linear regression. But before we jump into our presentation, let me tell you the order of the ones who's gonna present. The first one's gonna present is me, Salsabila Nur Syahla, with my student ID number is 18109333003. After me, Warisatil Ilmi is going to present with her student ID number 18109310117. After Ilmi is my friend Luthfiya Alifah is gonna present, and her ID number is 18109333004. And the last one's gonna present is Raihanil Jannah with her student ID number 18109322058. The introduction of the simple linear regression. Here are our main topics today. First, there's the introduction, then the method of least square, properties of the least square, the estimators of variance, assessing utility of the model, coefficient of correlation and determination, and using the model for estimation and prediction. First, we're gonna move into introduction. Before we start with what is simple linear regression is, we need to know first that there are two types of data in the context of statistical learning, which are independent variables and dependent variables. Independent variables are the data that can be controlled directly, and meanwhile, the dependent variables are the data that cannot be controlled directly. Now, we move into the introduction of the simple linear regression. In the context of this linear suggests that the relationship between dependent and dependent variable that we mentioned before can be expressed in a straight line. In other words, it involves estimating the mean value of a response variable y or predicting some future value of y based on knowledge of a set of related independent variables. Now, the model for the simple linear regression approximation leads to errors, of course. These errors cannot be eliminated, but it can be reduced. They are called as an irreducible error. With that being said, the equation of a line can be rewritten as we know before that the relation between the independent and the dependent variables can be expressed in a straight line. Of course, in order to do that, we need to make the both variables into a linear equation, which is y equals to beta 0 plus beta 1 x plus errors. Now, in this context, beta 0 and beta 1 are two unknown constants that represent the intercept and the slope. They are the parameters. Meanwhile, the e is the error term. Now, for the assumptions about the error, first, the mean of the probability distribution of E is 0. And then, the variance of the probability distribution of E is constant for all settings of the independent variable x. The third, the probability distribution E is normal. And the fourth, the errors associated with any two different observations are independent. Now, that is least square method. With this method, we can solve simultaneously two-year computing formulas for B0 and B0. So, we shall find B0 and B0, the estimates of B0 and B0, so that the sum of the squares of the residual is a minimum. The residual sum of squares is often called the sum of squares of the error about the regression line and is denoted by SSE. This means
minimization procedure for estimating the parameter is called the method of least square. Hence, the value of a and b should be found. With series of calculation, the value of b0 and b1 can be obtained with equation as follows. You can see this in the slide, the formula to find b1 and b0. Next, properties of least square method. First, an examination of the formula for the least square estimators reveals that they are linear function of the observed y value, y1, y2 until yn. Since it has been assumed that the random error is associated with this y value 1, 2, n are independent, normally distributed random variable with mean 0 and variance. It follows that the y value will be normally distributed with mean EY B0 plus B1 X and variance, and that B0 and B1 will process sampling distribution that are normally distributed. Next, the estimators of variance. The analysis of variance can be used to test for significance of regression. You can see the formula in the slide. Total corrected sum of squares is equal with regression sum of squares and error sum of squares. Suppose that we are testing the hypothesis. Hypothesis null is equal to 0 and hypothesis 1 is not equal to 0. The analysis of variance procedure for testing for significance of regression is by using the f-test or t-test. And this one is the formula to find f-test and t-test. You can see in the slide. The basic relationship between the t-distribution with f degrees of freedom and the f distribution with 1 and v degrees of freedom is t squared equal with f1, v. However, that the t-test is more flexible than f-test. T-test would allow testing against a one-side and two-side alternative hypothesis, while the f-test is restricted to a two-sided alternative. Confidence intervals on parameters. You can see both of formula in the slide. The first one is formula to confidence interval on the slope b1, and the second one is confidence interval on the intercept b0. You can see the difference between the formula. Under the assumption that the observations are normally and independently distributed. You can see at the slide, the up formula is confidence interval on the mean response at the value of x equal to x0, say mean y per x0 is given by, where mu y per x0 equal to b0 plus b1 x0 is computed from the fifth regression model. And last is prediction interval. Prediction interval on a future observation y0 at the value x0 is given by. The value of y0 is computed from the regression model y0 equal to b0 plus b1 x0.
Next, assessing the utility of the model. The table below is a simple linear regression model. A test of model utility is if the hypothesis is null is b1 equal to 0 and hypothesis alternative is b1 more than 0, it means it is one-sided on the right. So reject hypothesis null if the t less than the t alpha. Next, the hypothesis null is b1 equal to 0 and hypothesis alternative is b1 less than 0. So it means it is one-sided on the left. So reject hypothesis null if the t less than minus t alpha. Next, the hypothesis null if b1 equal to 0 and hypothesis alternative is b1 not equal to 0. So it means it is a two-sided and reject hypothesis null if the t is less than the t alpha per 2. Next, the coefficient of correlation. The quantity R, called the linear correlation coefficient, measures the strength and the direction of a linear relationship between two variables. The linear correlation coefficient is sometimes referred to a person product moment correlation coefficient in honor of its developer Carl Person. The mathematical formulation is shown on the slide. The value of R is such that R between minus 1 and plus 1. The plus and minus sign are used for positive linear correlation and negative linear correlation respectively. So there are three different types of correlation. It is positive correlation, negative correlation, and no correlation. Every type of correlation have a characteristic. The characteristic you can see it on the slide. For the knot, R is a dimensionless quantity, that is, it doesn't depend on the unit employed. A perfect correlation of plus minus 1 occurs only when the data points lie exactly on a straight line. If R is plus 1, then the slope of this line is positive, and if it minus 1, then the slope is negative. A correlation greater than 0.8 is generally described as strong, whereas the correlation less than 0.5 is generally described as weak. These values can vary based upon the type of data being examined. A study utilizing specific data may require a strong correlation than a study using social science data. The correlation coefficient R measures the correlation between X values and Y values in the sample. The population correlation coefficient is denoted by the symbol rho. So, as you might expect, rho is estimated by corresponding sample statistic R. Hypothesis null is R equal to 0. It is X contributes no information for the prediction of Y. And hypothesis alternative is R not equal to 0. It means two variables are at least linearly related. So, to perform this identical test is hypothesis null is B1 equal to 0 and hypothesis alternative is B1 not equal to 0. This is the formulation.
Next is test of hypothesis. First, one-tailed test. If h0 is rho equal to 0 and h1 is rho less than 0, it means reject hypothesis null if t is less than minus t alpha. If h0 is rho equal to 0 and h1 is rho larger than 0, it means reject hypothesis null if t is larger than t alpha. Second, two-tailed test. If h0 is rho equal to 0 and h1 is not equal to 0, it means reject hypothesis null if absolute value of t is larger than t alpha over 2. The formula of t is r square root n minus 2 over square root 1 minus r squared with v is equals to n minus 2. Next, the coefficient of determination. This quantity is a measure of the proportion of variability explained by the fit model. The analysis of variance approach makes us
makes use of the error sum of squares is SSE, which is sigma I from 1 to n yi minus y bar squared, and the total correct sum of squares SST is sigma I from 1 to n yi minus y hat I squared. The latter represents the variation in the response values that ideally would be explained by the model. The SSC value is the variation due to error, or variation unexplained. Clearly, if SSE equals to 0, all variation is explained. The quantity that represents variation explained is SST minus SSE. R square is coefficient of determination, which the formula of R square is 1 minus SSE over SST. R square is probably the most popular measure of how well a regression model fits the data. R square may be defined either as a ratio or a percentage. Since we use the ratio form, its values range from 0 to 1. A value of R square near 0 indicates no linear relationships, while a value near 1 indicates a perfect linear fit. Although popular, R square should not be used indiscriminately or interpreted without scatter plot support. Next is using the model for estimation and prediction. The most common uses of a probabilistic model can be divided into two categories. First, estimating the mean value of y, EY for a specific value of x. Second, entails predicting a particular y value for a given x. The difference in these two model use lies in the relative accuracy of the estimate and the prediction. For example, y hat equals to 2 plus minus 1.3 times x, while x is 3, so y hat is 2 plus minus 1.3 times 3 equals to 1.1. Sampling errors for the estimator of the mean of y and the predictor for an individual y is: first, standard deviation of the estimator y hat of the mean value of y at a particular value of x, say xp, is sigma y equals to sigma times square root of 1 over n plus xp minus x bar squared over ss double x. Second, standard deviation of the prediction error for the predictor y of an individual y value for x equals to xp is sigma y minus y hat equals to sigma times square root of 1 plus 1 over n plus xp minus x bar squared over ss double x. A 1 minus alpha times 100% confidence interval for the mean value of y for x equals to xp is y hat plus minus t alpha over 2 times estimate standard deviation of y. The formula can be seen on the screen. Thus, a 100 times alpha minus 1 minus alpha percent confidence interval can now be constructed from the statistic t equals to y minus y hat over s times square root of 1 over n plus xp minus x bar squared over ss double x, which has a t distribution with n minus 2 degrees of freedom. Then a 100 times 1 minus alpha percent prediction interval for an individual y for x equals to xp is y hat plus minus t alpha over 2 times s times square root of 1 plus 1 over n plus xp minus x bar square over ss double x. Thus, a 100 times 1 minus alpha percent prediction interval for a single predicted value y hat can be constructed from the statistic t equals to y minus y hat over s times square root of 1 plus 1 over n plus xp minus x bar square over ss double x, which has a t distribution with n minus 2 degrees of freedom.